everybody. So today what I'm going to talk to you about is delta S and how to calculate it. So I've introduced to you what entropy is, so you should have an idea from the previous video when entropy increases and decreases. But entropy actually has a numerical value just like delta H does. So I'm going to show you how to calculate delta S. And in fact, we could even use the reaction that we used up here. This was some work that we did in class. But we could even use the reaction that we did over here where we have C3H8 plus 5O2. So let's go ahead and do that so that we can calculate delta S for that. So if we were to do C3H8 plus 5O2 yields 3CO2 plus 4H2O. Now remember, we have a delta H for this, and our delta H value we used, just to go back and look, our delta H value when we did that was a total of negative 2,215. Okay, so we're going to put that over here because we're going to use this, negative 2,215, and that was kilojoules. So now let's go ahead and let's try and calculate the delta S. And just like we have the delta H, I had mentioned in class that we also have a value for delta S from our thermodynamics table. And so if we go ahead and we do that, let's go in here and look. So now we can find these values here. And so the third column is delta S. And so we can actually use that. So C3H8, when we go ahead and we do that, we're going to get negative 10, nope, we're going to get positive 269 for C3H8. So our delta, or our S value for this, is 269.8, and that's in joules per mole Kelvin. When we go ahead and we do this for CO2 and O2, let's go ahead and do that. And what I'm going to do is I'm going to pause the video. I'm going to write down these numbers so you don't have to go with me going back and forth. So I'm going to pause the video. I'm going to go through, write those numbers, and then we'll do the calculation. But what you would do is you'd go to the table and you'd look up each of them, just like I did C3H8. I went through and I found all the other values. And now, just like we calculate delta H, products minus reactants, we do the same thing for delta S. And so when we do this, we have delta S equals products minus reactants, so that would be 213 times 3 plus 69.9 times 4 minus 269.8 plus 205 times 5. Now notice something about this. I don't have a zero value for oxygen. It has a value. Now something else that's important, these are all gases. At least I use the gaseous water. And so when I look at this, I start off with 6 moles of gas, 5 and 1, and I end with 7 moles of gas. So the entropy should be, not a huge change. It should be slightly positive, close to 0. So let's give this a try. So let me type into my calculator here. We're going to have 69.9 times 4. Plus, we're going to have our 213 times 3. So plus, and then we're going to have our 213 times 3. And we're going to get a total for the products of 918.6. And then minus the reactants, we're going to have 205 times 5 plus 269.8. And so we're going to have minus 1294.8. So now when I go ahead and I try this out here, and I look to see what the difference is, let's see what my entropy change is. It's going to be slightly negative, which I find so interesting, 918.6. I wonder if I used the wrong value for water. I'm going to have to double check that. So when I do this, I actually get negative 376 joules per mole Kelvin. So it's slightly negative. Notice the value here is joules, not kilojoules, as it was for delta H. So we have a slight negative change here in entropy. Part of this could be due to the fact that the C3H8 is a really complex molecule compared to the other ones, although I'm surprised. I'm going to hold on for 1 second here. I want to check to see that I picked the right water. Okay, so when I went and checked, I did the wrong water. This water right here, instead of being 69.9, is actually 188, and that's the difference between a liquid and a gas. So this one should be 188. It's about that. So now let's recalculate this. So now we're going to have our 213 times 3, and then we're going to have plus our 188 times 4, and we're going to get now 1391. So that makes a difference, and enough difference that my prediction was right. So now if I do 1391 minus 1294, when I do that, I get 97, and it's positive. I just rounded to whole numbers. So this is 97 joules per mole Kelvin. So that complexity of that C3H8 didn't matter. I just copied the number wrong. This water was a gas. So here we have this situation, and I'm kind of glad. I was thinking about maybe redoing the video, but I sort of want you to see that the phase of the matter matters. Since we were using gaseous water, the entropy change was positive, compared to if we were using liquid water, the entropy for this change would have been negative. Okay, so this is how I calculate my delta S. Now, why do I care about this? Why is this important? Well, it happens to be important because we want to tie the two together. Remember, what I said in the previous video was when we become more stable, we release energy, we're exothermic, and we increase the entropy. And this ties together in this equation here called the free energy equation. The free energy is given the symbol delta G for Gibbs free energy. The Gibbs free energy is equal to the change in the enthalpy minus the Kelvin temperature times the change in the entropy. You can also calculate delta G directly by using the table and do delta G of the reaction equals delta G of the products minus delta G of the reactants. Now the SAT exam asks you about doing this qualitatively, and that's what I have this table down here for. But if you're doing Regents, they don't really ask you about delta G at all. They just want you to know the general idea, and they especially want you to know this first condition here, where you're stabilizing both the delta H and the delta S. Now, how does this work in terms of calculating delta G? Well, the general rule for delta G is as follows. When delta G is equal to a negative number, the reaction occurs spontaneously. And when people think of spontaneously, they think of something happening very, very quickly. But that's not the case. Spontaneously in chemistry just means that it is favorable, meaning that it will happen if you give it enough time. It could be slow, it could be fast. It's unclear how long it is. This doesn't tell you anything about the speed of a reaction or how fast it is. So when delta G is negative, it's negative because of the values of delta H and delta S. Remember, we said that delta H, when it is favorable, it'll be negative, it'll be exothermic. Delta S, when it's favorable, it'll be positive. Notice, when we have delta G, when we look at delta G for these delta H and delta S values, delta G is negative. Negative means that it occurs spontaneously. It means that the reaction is favorable. That means that the reaction is always favorable. If you had a delta H that's positive and a delta S that's negative, the delta G would be positive always, and the reaction would never be spontaneous. And then the interesting conditions happen down here, where you have a positive delta H, which is not favorable. So this would be unfavorable. And you have a positive delta S, which is favorable. So you have the two conditions fighting each other. And when we have those two conditions that are fighting each other, where we have positive and positive, delta G could be either. And it's only going to occur spontaneously when you're at high temperatures. If you had a situation where they were both negative, now you have the opposite happening. Now you have this condition being favorable and this condition being unfavorable. So the delta H is favorable, the delta S is unfavorable, and that will be spontaneous only at low temperatures. And we can go over specific examples in class to see that. But let's tie this into our reaction. So our reaction that we did with our C3H8 up here, let's zoom out, our C3H8 up here, it had a delta H that was negative. Delta H equals a negative value. And it had a delta S, which was positive. This means that this reaction will be spontaneous always. If we want to calculate the delta G, we can plug in the values. Delta G equals delta H, which is negative 2,215 kilojoules, times, minus temperature, we'll give it a 298 temperature in Kelvin, times the entropy. And this is where you got to be careful. The entropy's units have to match. And if you notice, they don't match over here. They're joules versus kilojoules. So we need to get, you could change either one. I'll change the entropy. We'll times this by 0.097 kilojoules per mole Kelvin. So when we do this, what you'll see is that we will get a negative delta G. That negative delta G will allow us to see that the reaction is spontaneous. So let's go ahead and do that. 298 times 0.097. We make that a negative value, and then we subtract from it 2215, and we get negative 2,243 kilojoules. We could say per mole, really, because this is per mole, and this is per mole. And this is our delta G value right here. And that value is our final value for delta G. And that tells us that the reaction is spontaneous. Now again, I could do a delta G problem in which in this case I had to find delta H and find delta S. But I could also look on table, C, the one that's from the textbook. And so I can do that by doing delta G products minus delta G reactants. And so that will give us our delta G for our reaction. All right, what I want you to do is try this problem out. Let me know how it goes, and tomorrow we'll go over it in class, and we'll also practice some more of these as well. All right, thanks so much for watching.